What's up guys, this is Masi, welcome to my channel. In previous videos I talked about acids and bases, and I started with definition of acids and bases, the difference between Arrhenius model and Bronsted and Lowry model, and I also showed you what are conjugate bases or conjugate acids, and then I defined the acid dissociation constants, which is Ka, and showed you some acid dissociation reaction. And also we learned Bronsted and Lowry model is not limited to aqueous solutions, it can be extended to reactions in gas phase. So I want to talk about acid strength in this video. The strength of an acid is defined by the equilibrium position of its dissociation or ionization reaction. As you see here, this equation Ha plus H2O gives H3O plus and A minus. So as you see here on the left hand side we have acid and water. Water acts as a base in this example, and the right hand side you will see the conjugate acids and conjugate base. H3O plus is water after it gained proton, so it becomes H3O plus, or we call it hydronium ion. And then we have also A minus, which is the conjugate base. So after acid loses the proton, it becomes A minus, which is the conjugate base. So what is strong acid? Strong acid is one for which this equilibrium lies far to the right. This means that almost all the original Ha is dissociated or ionized at equilibrium. So whenever we have a strong acid, when it dissolves in water, it dissociated completely into its conjugated base and conjugate acid. So there is no original acid left in the solution. So Ha becomes hydronium ion and A minus completely. So when we are talking about the previous reaction I showed you, this will be one-way reaction. It's going to be irreversible reaction. So it lies far to the right. So when we are talking about dissociation constant, which is Ka, it's going to be a very large number. So we don't normally define Ka for strong acids. So Ka is basically for weak acids. So strong acid and weak conjugate base. This is an important connection between the strength of an acid and that of its conjugate base. Strong acid yields a weak conjugate base, one that has a low affinity for the proton. So it means that when I go back to this reaction again, Ha, when we have a strong acid, when it loses the proton, it becomes A minus. This A minus, it has very low affinity to gain proton. You know, bases tend to gain proton, but A minus doesn't have a high affinity to gain this proton. That's why we call it a weak conjugate base. So as strong acid results in a very weak conjugate base. So as you see here, that shows strong acid result in weak conjugate base. So when we have a very strong acid, we have a very weak conjugate base. So as you go down from very strong acid to very weak acid, you finally have a very strong conjugate base. So when the strength of an acid decreases, the strength of the conjugate base increases. And also in this slide, you can see the difference between strong acids and weak acids. The top one is for strong acids. As you see here, before dissociation we have completely Ha, 100%. After dissociation, as you see here, is completely dissociated into its ion, like H plus and A minus, completely dissociated, and there is no original Ha left in the solution. But whenever we have a weak acid, as you see here, it's mostly undissociated, and we have it like almost the concentration of original HA is the same as concentration of HA after dissociation, and we produce just a little bit of H plus and A minus. That's why we call it a weak acid. A weak acid is one for which the equilibrium lies far to the left. Most of the acid originally placed in the solution is still present as HA at the equilibrium. A weak acid dissociates only to a very small extent in aqueous solutions. So whenever we have weak acid, most of it still remains after the dissociation, and we have very small amount or concentration of conjugate acid and conjugate base after the dissociation. So as we said earlier, a strong acid has a weak conjugate base, so a weak acid has a conjugate base that is a much stronger base than water. The weaker the acid, the stronger its conjugate base. This slide, I have some common strong acids. We have sulfuric acid, hydrochloric acid, nitric acid, and perchloric acid. So all these strong acids, as I say, is dissociated completely into its ions, into conjugate acid and conjugate base. However, weak acids, we have equilibrium, we have two-way reaction, reversible reaction, and most of these acids remain completely untouched after the dissociation, and we will produce just a little bit of the products. Usually 5% or even less than that remains after the dissociation. So whenever we have smaller number for Ka, it means that we have a weaker acid. Whenever we have larger number for Ka, it means that we have a larger dissociation constant. So it means that we will produce larger concentration of its product. I hope you enjoyed this video. Please leave me a comment if you have any question. If you find it useful, please like this video, and also you can subscribe this channel. You can find lots of videos regarding math and science. Thank you for watching. Have a great day.